This two-part presentation will focus on the practical diagnostics that we can do with modern production analysis. In the first half, we'll look at the theory of why we should do modern production analysis at RTA and the diagnostics that we can get out of it. And in the second half, we'll have a software demonstration. We'll look at some of the errors that rate transient analysis can help uncover, and also look at some of these diagnostic capabilities in detail. To start off with, we'll look at the traditional methods so we can have a clear contrast to what production analysis or RTA is all about. The traditional methods, i.e. using the ARP's decline curves, have been the cornerstone of reserves evaluation and production forecasting for many years, particularly in North America. The traditional decline curves use production rate only and rely on historical conditions being maintained through into the future. Implicitly, they assume constant operating conditions. They're empirical by their nature, with no actual theory behind them, and based on analogy where you see how the well is performing and forecast from there, and do so for similar wells. The deliverables generated from this type of analysis are the production forecast and recoverable reserves under current conditions, with the advantage being that we can get a handle on these deliverables very quickly. There are limitations to these methods, such as when a well is rate restricted, when the rate is being kept constant. Due to the nature of this, we cannot forecast from here. Another case would be, say, if the well is put on compression. Any forecast produced would now no longer be valid. These types of scenarios are handled excellently with modern production analysis, which we'll start looking at. Modern production analysis, or RTA in comparison, uses both rates and flowing pressures and is based on physics, not empirical methodology, and uses analytical models where we want to understand the fluid flow in a reservoir. And this is actually something pressure transient analysis has been doing for many years, and production analysis methods are based on these PTA techniques, just using them in a different way. Production analysis involves a reservoir signal extraction characterization, where we take a large amount of data and then analyze it to see if there's a reservoir signal that we can extract. In a way, it's like a forensic analysis of the data. We get the same deliverables as the traditional methods, but get quite a bit extra. So now we can get the original gas in place, original oil in place, and as it's derived from performance data, we can therefore get a performance-based recovery factor. So it can easily do screening, see which wells may have a low recovery factor, and hence see which wells may need our attention and potentially do some production optimization. Drainage areas can also be determined, and if we know the spacing of the well it was drilled on, but we might want to carry out some infill drilling and drill some more wells. In addition to this, RTA will also give us parameters such as permeability and skin. Modern production analysis, RTA, is integration knowledge that allows us to get a bit of the well test side and a bit of the empirical side, as well as producing its own deliverables such as the performance-based recovery factors, flow regime, characterization of the entire life of the well, as well as being able to analyze transient data from tight gas wells. So this means we no longer have to shut in the well for incredibly long periods of time to get the results we require. So why should we use modern production analysis at RTA? The biggest reason for doing it is to evaluate and confirm reserves as soon as possible, and sometimes there is upside that you don't see with traditional methods, and it goes the other way around and avoids you overbooking reserves. So it actually helps uncover some errors. Production engineers may use RTA to monitor production performance, And once they've got a good model match and understand the reservoir, they can update this model going forward and see if the actual performance matches the performance of the model. As soon as there is fall off or divergence between the two, they can go in, take appropriate measures, and do something with the well. In this respect, it's acting as an early warning system. Also, if only rate was being monitored, a drop in rate may be thought to be a change in productivity, when it could just be, say, a change in back pressure. RTA, though, allows us to quickly see what is going on. RTA can also be used as an alternative to full pressure transient analysis to characterize the reservoir, and can be much more economic as we do not need to shut in the well. This is particularly important in low permeability reservoirs. It also allows us to see much further into the reservoir than PTA may normally allow. Another reason to use RTA is that this data should be collected as part of good production practice, and these techniques can easily be implemented into an engineer's workflow. With the data in harmony, it may take an engineer only, say, 10 to 20 minutes to do a Typecurve and model match, and then you have an answer and can make a decision. So there's a very low cost of effort involved, especially when it comes to the time it takes to do, say, a full numerical simulation. This is not saying that we should not do numerical simulation, but RTA acts as a very good precursor to it, and also provides quick checks to the continual health of the well. So within IHS RTA, what methods can be used? We have the flow material balance, type curves, analytical, numerical, and our new hybrid models, a tool that helps us to get permeability and fracture half-length through the unconventional reservoir module. And we also have our probabilistic and sensitivity module to carry out probabilistic modeling using Monte Carlo simulation. And we'll briefly look at some of these methods now. Here's a type curve from the software, and this is a Blassinger type curve. But there are many others available, such as Abel-Gardner, Fetkovich, NPI. And when we plot the performance data on a type curve with no reservoir response, and position the data to get a match, we get bulk reservoir parameters to help characterize the reservoir. Also important is the qualitative interpretation, where you can distinguish, say, between transient and boundary dominated flow. Because until we get to boundary dominated flow, we do not really know the total contacted pore volume, and hence we don't really have confidence in what a recoverable reserves could be or a long-term forecast. What is also important is the diagnostics that we can get out of these type curves, which we'll move on to shortly. The flow material balance is a very popular and simple method that takes performance data and extrapolation of data trend within boundary dominated flow gives the original fluid in place. This method is very useful because it uses flowing pressures rather than static pressures. So it means you don't have to shut in the well and perform a build-up. This is particularly important in low permeability reservoirs where it may take an incredibly long amount of time to let these wells build up. And this methodology was developed in-house originally with Louis Matar and Ralph McNeil in '98. Once we've got our bulk parameters, say from type curves, we can then use models to validate our interpretation with our history matching, and then we can forecast from there. This is an analytical vertical model, but there's also numerical models for a wide range of completions. Our recommended workflow for production analysis is based on the SPE paper written in-house in 2003, and the concepts put forward then are still vitally important today, and this is the workflow our engineers religiously follow. The first step is diagnostics, where we inspect the quality of the data. Then after we've done that, we qualitatively identify certain features of the data, say our type curves, which teaches about the well and the reservoir. The next step is interpretation and analysis through type curves and the flow material balance to estimate reservoir parameters and identify flow regimes. Once we've done that, these parameters then are put into a model to get a history match, which is then followed by forecasting and optimization scenarios. There's also a feedback loop here, because sometimes we make an interpretation that does not get a model match. And so we need to go back and revise the interpretation, as all these things need to make sense. Every time you do rate transient analysis, you learn something new. And it's important to treat each well as an individual and try to learn as much about it as possible. This is not always practical, as there may not be enough time to do this, but for new fields you want to spend time with the data to understand it as much as possible. If it's early on in the life of the exploitation of the reservoir, you want to learn how to develop the field. Thus, it's wise to put an effort up front. Once you're in full development mode, with many wells being drilled, then it may be prudent to start applying more of a cookie product approach to some of your wells. So to start understanding data, we need to do diagnostics. So what are diagnostics? They are a qualitative investigation of the data that is pre-analysis and pre-modeling, and they must be quick and simple. They're also a vital component of production analysis and reservoir engineering in general. We need to make sure the time is taken to understand what is going on in the reservoir to ensure that results are meaningful. Otherwise, it's a case of garbage in, garbage out. The first case we'll look at is to do with diagnostics of the data itself. We're inspecting the quality of the data, and this is something that's very easy to do within Harmony. So let's look at this data set. As you can see, this is a pretty high deliverability well, and both the rates and pressures are fairly flat. Measurement of the pressure looks good, as it's being updated on a regular basis. When you see times where pressures are being held constant, we need to question the validity of the data. So we took this data, performed the analysis, and it shows that we have a very large reservoir with a minimum contact volume of 90 BCF, as we're still in transient flow. So this well has not hit boundary dynamic flow, so the reservoir could be much bigger. And it's also determined from that analysis that due to the match of the type curve, there's damage to the reservoir and would have a high skin. However, remember this data set where both the rates and pressures were flat. This should have sounded as a bit of an alarm bell. Rates and pressures always come in a pair, and if the measurement is being done correctly, they should be changing at roughly the same time. So we should always look to see how they're changing with respect to each other, and there's three ways that this can happen. First is that there's no relation between the two, and this is not right. Second is may look like this, where they track each other but in the same direction, i.e. rates go up, pressure go up. This is not right either. Thirdly, in the correct relationship is where they track each other in opposite directions. The rates go up and correspondingly the pressures go down and vice versa. Because when you draw down on the well, the lower the sand face pressure, the greater delta P. As we know from Darcy's law, the rates increase. So from this very quick diagnostic, we found out something was wrong with the data, and so prevented a false interpretation being made. It turned out that the rate data was correct, but the pressure data was being collected incorrectly, and it turned out it was a gauge on a downstream side of a choke, and no way connected to the reservoir, and just really representative of line pressure. However, we managed to get a hold of the correct pressures, and when these were analysed, it turned out the reservoir was actually much smaller, with only 19 BCF original gas in place, but still quite damaged. Thus, performing this incredibly quick diagnostic prevented a false interpretation being made and a major overbooking reserves, and also taught the company that the wrong data is being collected out in the field. The great thing about doing production data analysis is that it always teaches something new. And we'll now move on to Typecurve Diagnostics. The next step is start looking at diagnostics on log-log plots, with the reason being that you can learn a lot about flow regimes and what is happening with data that you not see in a linear plot. As you can see, transient flow is easily identified by the upward concavity and boundary dominated flow is easily identified by the downward concavity and unit slope. In an ideal world, all the data should line up on this plot. Unless you're very lucky, this may not happen. So we can do diagnostic analysis to see what is causing this. The first diagnostic we get into is material balance diagnostics, and they're termed as such because these are things that happen over a long period of time when the well's in full boundary dominated flow and take a long time to develop and happen diffusely over time. This plot is just the same as a Blasingame type curve plot with a normalized rate versus material balance time. The unit slope on this plot represents volumetric depletion, and if the data is lying in the slope, then the well is draining like a tank in boundary dominated flow. And there's only really two options that can happen here that's different to this unit slope. One is that the data can drop below the unit slope, and the other is they can drift above the unit slope. If it drifts away from the unit slope, this is evidence of pressure support, such as water drive, connected gas system, composite systems, multi-layer or solution gas evolution. And these are things that provide recharge over time. And if the data moves away, it becomes clear with this diagnostic that we're not draining a volumetric system, and draining some kind of system with influx on the boundary. We can't tell what the influx fluid is, we just know there's an increase in energy. However, this diagnostic has quickly told us that there is pressure support and allows us to start asking the right questions of ourselves to find out what is actually causing this. If the data falls off the unit slope, we have a leaky reservoir and its interference. So if a well was drilled in a reservoir, it was only wells in volumetric depletion, and then another well was drilled and started draining, it would then reduce the available drainage area to the first well and its interference. And this is shown up as the data falling below the unit slope. Both of these two scenarios are incredibly common, and this diagnostic is powerful as it very quickly tells us immediately whether either of these are going on or not. Unlike material balance diagnostics, productivity diagnostics are going to be short-term and have much more obvious effects, with things occurring near the wellbore or actually in the wellbore. And we'll continue to use the Blasingame type curve to illustrate these points. A well cleaning up is easy to identify. Here the production rate and pressure might be increasing at the same time, because here we're getting relative permeability effects, we're getting production of completion fluids, and any single phase type curve is going to tell us this is not possible. So we can't really do anything with this data until after cleanup we start to line it back on the slope. And at this point in time, then we'll use this area to extract the reservoir signal. Liquid loading is very common, and we'll see it in low rate gas wells, and looks very similar to interference, but is very different due to build-up of water or condensate in the wellbore that increases the pressure drop and increases the time. It gives you this signature. If we get a parallel trends in the data, we mean we're getting a productivity shifts. Where at some point in time, something happened, operator's gone in, perhaps done a workover, or changed out the tubing. There's a step change in productivity because something has happened. A step change in pressure, say a well is put on pressure, shouldn't have this effect, because we're changing the production rate and the flowing pressure accordingly, and the normalized rate remains the same, as it's just a change in back pressure. However, if you actually change the productivity of the well, such as by stimulating or changing the number of perfs or the tubing string, you will see these parallel shifts. Productivity diagnostics, that we just discussed, are things that happen due to operational phenomena, or things that happen in or near the wellbore. Transient diagnostics are things that happen in early on in time, However, in low permeability reservoirs, these things may take a long time to happen, and transient flow in low permeability systems is like being stretched out in time. There are three main ones here we'll discuss. Radial flow of a vertical and fracture well will be identified by lining up an output concavity with varying degrees of concavity, and this depends on the amount of damage at the well. If it's very damaged, we have very flat at the beginning. When we have a fracture well, we should expect linear flow. And on a normalized rate versus material balance time log plot, this appears as a half slope, showing us 2 log cycles across for 1 log cycle down. Unlike the unit slope, which is 1 log cycle across for 1 log cycle down, as you see here in the volumetric stem. This is also different from radial flow because it does not have the upward concavity. We also get transitionally dominated flow when we say move from radial flow to linear flow in a channel system, and you may get data does not line up well on type curves. It may look something a little like this. The final diagnostic I want to discuss is the bad data diagnostic. As the data used for these type curves is initial pressure, flow pressures, and rates. Normally rates are okay because saying the gas or the oil, so you have a good idea how much pressure, and we generally have a good idea how much pressure you have. We might run into difficulties in the calculation of bottom hole flowing pressure if they're under or overestimated, or the initial pressure is not correctly known. When a delta P is too high, you may see something like this, where data doesn't line up on the type curve, and this could be due to the tubing size too large in calculations, initial pressure too high, or the wellbore correlations are underestimating the pressure loss. When the delta P is too low, you may see something like this, where slope is too steep for any normal reservoir signal, and it's caused by the tubing size being too low and too small in calculations, initial pressure too low, or the wellbore correlations may be overestimating the pressure loss. This concludes the theory section of the practical diagnostics for RTA, and we'll shortly move on to the software demonstration.